So when we're working on inclines, things get a little bit different, okay? So what we're going to do is if something's on an incline, we're going to take our regular X and Y axis and we're going to kind of tip them. Okay, so this is if something's like on a ramp or something like this. So here in our flat surface, usually our X is horizontal and our Y is up and down. So now on an incline, we're going to think of our X and Y as differently. Okay, so we're kind of just going to take this and tilt it. And so now our X is parallel to the ramp and our Y is going to be whatever's perpendicular. Because now that it's not sitting on a surface or anything like that, now we have that incline, we really need things in terms of what's happening parallel to the incline and what's happening perpendicular. Because we know things like, our applied forces will most likely be up and down the incline. Our frictional forces will definitely be up and down the incline. And then we know that there's a component of gravity. Now this is on an incline. Gravity still goes straight down, and there's a component now that's going to be pulling this down an incline, which is, if an incline is great enough, something's just going to naturally roll down it or go right down it. And that's because now there's a component of gravity that's parallel to the incline. So that's what really makes it different, is that gravitational force pulling it down, because of course, force of gravity is straight down. But now it has that kind of component in the X and Y direction, right? Because FG, no matter what you do, is going to go straight down towards the ground. So the problem is it's actually pulling it down the incline a little bit. So we have to break it down into the component that's perpendicular to the incline and parallel to the incline. Because the bit that's parallel to the incline is pulling it down the incline. And that's really, really important for us to look at. So that's what we're going to call our FG in the X direction now. And this is going to be force of gravity in the Y direction. Okay? So that's what we're going to do when we have force of gravity. We're going to set it up into its X and Y directions. Remember, X is parallel to the incline, Y is perpendicular to the incline. Okay? So if this is my angle right here, as that increases, the force of gravity in the X direction increases and the force of gravity in the Y direction decreases, right? Because as this increases, it's becoming more and more vertical, okay? So that's really, really important. And then we know, of course, normal force we know is what's equal and opposite to gravitational force. But in this case, normal force would be going straight perpendicular. So therefore, normal force is going to change with that gravitational force in the X direction. Because say that's my box or whatever, then my normal force is also perpendicular here. So that is going to change as our force of gravity changes. It's not really the correct distance here, so I'm going to redo that. The correct length, so it should be about equal to FGY. So there's FN. So that's going to vary with FGY as well. So really important that we note that. Another little thing I want you to note, if we have the incline angle, we actually have an angle on this other right angle triangle here with all the FGs, and that is this one. Those two angles are the same. If you would like to know why, it has to do with similar triangles, and we can discuss that. You can ask me that in person if you would like to, okay? Or ask your teacher if I'm not your teacher, but you're still watching this, then ask somebody why that's the same if you're really that curious. It does have to do with similar triangles. So let's do a few examples and get into that, because this is when things get kind of crazy. We're going to have to figure out, okay, well, we're not just in one dimension anymore. So we're going to have to figure out our force of gravity in the X and Y direction, that parallel and perpendicular. So it's really important that you're drawing your free body diagram correctly and then just paying lots of attention, okay? So we have a 6 kilogram block. First, it's at rest on a 25-degree incline. And I want to know what minimum coefficient of friction is necessary to prevent the block from from slipping. What the heck does that mean? That means we don't want it to move. Okay, so what minimum coefficient of friction could we have here that would mean this would stay in place and that friction would perfectly counteract the gravitational force in the x direction? Okay, so let's take a look at what we have and what we know. So obviously, always first step, draw that free body diagram. Okay, so here we go, block on an incline, of course, because why else would we do anything else? We have our angle of the incline being 25 degrees. And of course, we want to know what is working in what direction. So we know normal force is perpendicular to the surface. My force of gravity is, of course, always going straight down. But as we just saw, that means that I have a component in the y direction. So I'm going to call that y. And in the x direction, I'm going to call that FGX, meaning x is perpendicular to the incline, y is parallel to the incline. Nope, other way around. FGX is parallel to the incline and FGY is perpendicular to the incline. We're doing great. I'm not messing you up at all, I'm sure. And then, of course, we know that 25-degree angle is also right there. Okay, so we want to know what's going to make this stay where it is. Well, force of gravity in the x direction is working down the incline, so obviously force of friction has to be moving against that motion. So it'll be going up the incline just like that. And that's everything, because we just want it to be at rest. So there's no other forces at work to make it be at rest. Okay, so again, we're going to find the minimum coefficient of friction, and we're going to assume that all our accelerations are 0 because we want this to be at rest. And that's going to be so nice. Okay, so now when we're working with our x direction, or sum of forces in the x direction. Why am I starting with the x direction? I don't know. I'm just going to start with the x direction. Honestly, sometimes you just have to start somewhere and then see where it takes you and go until you can't, and then go to the other direction and then go until you can't, or gets you somewhere else, and then you go from there. So honestly, just do do Newton's second law in one of the directions until you can't go any further, and then go to the other direction. We need to define a direction as positive. Since nothing's moving, it doesn't actually matter. So since I'm working with the x direction, remember x is parallel to the incline. So that's up the incline or down the incline needs to be positive. So let's go ahead and say up the incline. Okay, that's going to be positive this time. So I'm going to do all the sum of forces in the x direction. I have force of friction going up the incline, which is positive. So I'll start with that. I have force of gravity in the x direction going down the incline, so I'm going to subtract that. And I know that I'm looking for when this block is standing still, is not moving at all, so my acceleration is 0, so therefore mass times acceleration is all 0. So that makes life nice and easy. Okay, what do I mean when I say go until you can't anymore? Well, I do know that force of friction can be broken into another equation. That's mu times the normal force. Okay, so that's not bad. And then FGX, well, FG is mg, mass times gravitational acceleration. So a lot of people just want to be like, mg, I'm good, yay. Wait. No, we have a little right angle triangle here, which is just lovely, isn't it? So FG here is actually our hypotenuse. If we take a look at this triangle a little bit closer up, here's our right angle triangle, here's FG. FGX is opposite this angle that we have, that 25-degree angle. So that, if I want to get force of gravity in the x direction, I need to take force of gravity and multiply it by sine of theta. So force of gravity is mg, and then I multiply that by sine of theta in order to get the force of gravity in the x direction. Okay? And of course, you can probably guess how we're going to get the y direction. We're going to multiply by cosine of theta. Okay, so there we go. We kind of broke our two equations down into the other equations that we know, and now I'm stuck. Now I'm like, I don't know where to go. I need to find mu. It's right there, so it's there, but what the heck is Fn? M, we have that. G, we have that. Sine theta. Well, we can find we know what theta is. So it looks like that Fn is bugging us. Oh, I think I know a way to find Fn. Usually I have to go over to the y direction to do that. So that's what I'm going to do. So here the y direction is perpendicular to the incline. And I'm going to go ahead and say, well, we might as well define the direction of the normal force to be positive. Again, if something's not moving, then I don't care which direction is positive or negative. You can choose. And again, since this is staying still, it's not moving up or down or off the incline. Again, I know that this is 0, so that helps me. So in the y direction, I have normal force in the positive, and then force of gravity in the y direction is negative. So I'm going to subtract that, and that should equal to 0. So what does that mean? Oh, I can get normal force. Normal force is equal to force of gravity in the y direction. What's force of gravity in the y direction? Well, force of gravity is mg, and then like we said over here, we get y direction by multiplying by cosine theta because it is the adjacent side, okay? So there I'm going to say cos times cos theta. Well, that's a little bit helpful because the only thing I didn't know over here was Fn. So here I can take this and substitute it in for Fn. Isn't that nice? So that's what I'm going to do. I'm going to go over here and put that in there and say, okay, well, that'll help because then I just have everything that I know, and the only thing I don't know is mu. Oh, that's exactly where we want to get, where we only have one unknown. That's always the best. Mg cosine theta, okay? And I'm going to go right to adding mg sine theta to the other side because, well, it's just getting too crazy to just say it constantly, say that's equal to 0. And at the end of the day, we know that we're looking for mu. Okay, so I divide both sides by mg cos theta, and this weird thing happens where mg's cancel out. So I didn't even need those this whole time. Are you kidding me? Okay, so mu is actually equal to sine of theta divided by cosine theta. So again, it would actually be mg sine theta over mg cos theta, but the mg's cancel out. And now some of you probably don't know this, actually a lot of you, because you haven't taken Math 30 yet. This is a really special trigonometric identity, okay? So I'm going to talk about that for a minute. There's this special trigonometric identity that you learn in Math 30, but you guys are going to learn it early because you're in Physics 20. And that is that sine of theta divided by cosine theta is equal to the tangent of theta. So that's a very special trigonometric identity that you learn in Math 30. Really quickly, if you think about it though, what is sine? Sine is opposite divided by hypotenuse. And then I divide that by cosine theta. What is cosine theta? That is adjacent divided by hypotenuse. What's that the same as? Opposite over hypotenuse times hypotenuse over adjacent. Oh my goodness, what happens? Look, it's opposite over adjacent. So that is something that you can actually prove yourself really, really easily, that sine over cosine is tan of theta. So obviously, could you just put mu is equal to sine theta over cos theta or sine 25 over cosine 25? Of course you could. Please do. But also, you're going to need this fact because it is going to help you in the future, that sine over cosine is tan, and it does make your life a little bit easier coming up. So that is just a special property. And so this minimum coefficient of friction to prevent it from slipping is just the tan of 25 degrees. All that work for just the tan of 25? Are you kidding me? So that is 0.466. And there we go. There's our coefficient of friction. We're done. So these questions, prepare for them to all look like this, except for even more complicated sometimes. Okay? There's a lot of work, but I promise you, go through the motions, do the free body diagram, sum the forces in the x direction, and go until you're like, okay, I'm stuck. I don't know what else to do. Go to the y direction, sum all the forces, go until you're stuck. And then be like, then look at the two of them and see how they relate, right? And then just keep going kind of back and forth. And the more you do that, the more you'll kind of start seeing patterns. So we're going to actually do 2 more examples here. So buckle up because there's quite a few here. All right, so now we have a 9 kilogram block. It's being pulled up a 32-degree incline. Okay, so we actually have an applied force going up the incline now. Okay, and this is happening at a constant speed. Oh my goodness, that's so important. Why is that so important? Why is it important if something's at a constant speed? What is the acceleration if something's at a constant speed? It is 0, and that is so important. So yes, there's an applied force here. But guess what our net force is still equal to in the x direction? 0, because it's a constant speed. So that's going to be pretty important for us. Okay, let's start with a free body diagram. I know I haven't finished even reading the question, but I just want to do the free body diagram first because it's nice to be able to put the information down as you go rather than just like reading it and being like, huh? So that's what I like to do. I already know that I have an applied force going up the incline, so I'm like, I just want to draw that. So let's do it. So applied force up the incline because it's being pulled up the incline at a constant speed. Coefficient of friction, which means we have friction. Friction always opposes the motion. So since it's being pulled up the incline, I'm guessing friction is going opposite that, so it's going down the incline. Okay. We want to determine the applied force necessary to pull this up at a constant speed. Okay, obviously our free body diagram is not finished. Okay, we have normal force going upwards, or not upwards, perpendicular to the incline. Our force of gravity is going straight down. But of course, we don't want things that are going straight down. We want perpendicular and parallel to the incline. So I have to break that up into the perpendicular part, which is y, and the parallel part, which is x. There we go. There's my beautiful free body diagram. Okay, so again, if you don't know where to start, just start with the x direction. Here, again, I don't have acceleration, so it doesn't matter which way is positive. But since it's moving up the incline, I'm still going to go ahead and say up the incline is positive. And I'm going to sum all the forces in the x direction, which should equal to mass times acceleration in the x direction. Okay, so what forces are in the x direction? Obviously, the applied force is moving up the incline, so that's positive. And then I can subtract the force of friction from that. Now, most people will stop there and will forget about something else that's pulling it down the incline. And that's totally understandable because the vector is all the way down here. Okay? So please don't forget about force of gravity in the x direction. It is, in fact, pulling it down the incline, and we do need to include it. So, and then, of course, we know acceleration, since it's moving at a constant speed, is 0. Okay? So, like I said, kind of just break stuff down until you get stuck. So, I know that there's an, well, I don't know the applied force. I know there is one, but I don't know what it is, so I'm just going to keep that FA. By the way, I'm going to add FF and FGX to the other side because, yeah, it just looks messy like that. Then furthermore, I can break down force of friction. What is force of friction? Is always mu Fn. I don't have Fn, so I'm going to have to find it. Fgx, well, again, the x direction. Well, here's my angle right there, so it's in the opposite side. Oh, right, so that's Fg times sine theta. Furthermore, Fg is always m times g. So, and then times that by sine theta to get your x direction. And, okay, so I'm looking for applied force, so can I find it? I have mu, I don't have Fn. Okay. I have mg, I have a mass, and then g is a constant. I have the angle, so I have almost everything except for Fn, so, oh my goodness, I wonder if you're starting to maybe notice the pattern here? Guess what we have to do to get Fn? We have to go over to the y direction. Hopefully you are noticing a pattern, because this really is like the pattern. You do just have to keep going back to the y direction to get the normal force. But make sure if you're on an incline, you don't just make normal force equal to mg, because it is not. Okay, so normal force is positive here. I made perpendicular upwards of the incline, positive, so Fn is positive, and then my FGY is negative. And how do I get FGY in the x direction? Well, first of all, wait, I said too much there. Let's take this step by step. I'm just getting ahead of myself because I'm so excited about physics, you guys. First of all, acceleration in the y direction. Is this thing moving off of the incline? No, it's 0. Okay, we can count on that. I don't know that I've ever encountered a situation in which the box is actually going to physically move off the incline. So we don't have to worry about that. So no, it's not moving there at all. So we know that normal force, since normal force minus the force of gravity in the y direction is 0, normal force is equal to the force of gravity in the y direction. But keep in mind, that's not just mg, which so many people want to say. Because it's on this side of the right angled triangle, it's not the hypotenuse. The hypotenuse is FG, so I need to multiply that by cosine theta because it is the adjacent side. Okay, well now I can use that and put that in for Fn, so that is what I'm going to do. So now instead of Fa equaling mu Fn, I'm going to have mu times mg cosine theta plus mg sine theta. Okay, and I know here now you're going to want to do some canceling out of stuff because we got to last time, but it doesn't work that way because we don't have mg like in every single term, so I cannot cancel out the mg's. I'm sorry. I know you want to, but that only works when they're like on both sides and part of every term, and that's not the case here. So we just have to actually plug all these numbers in. So it's going to be a bit of a monster to plug into your calculator and to plug the numbers in, but we can do it. Mu is 0.36, m mass is 9 kilograms, g is 9.81 meters per second squared, cosine of theta, that's 32 degrees, plus mass again. And yes, when you do this step, you should always be putting in units. Come on. Be a real physicist. Theoretical one, at least. Okay. Am I done yet? Oh my goodness. That took forever. Okay. Applied force. Let's figure out what that is. When you put that in your calculator, please make sure you put like a big set of brackets here and do 0.36 times 9 times 9.81 times cos 32, close bracket, and then close that bracket, plus, and then do another big bracket here, 9 times 9.81 times sine 32, close that bracket, okay? And you should get 74 newtons. There is your applied force. So it's a lot of work to get there, but we got there eventually, and that's what matters. Okay, so hey, and I still think this doesn't even take up a full page. So until your solutions take up a full page, you're officially not allowed to complain. That's just a random rule I made up. Let's see if we can get to a full page with the next one. Won't quite get there, but we'll get close. So, do I need to say anything else about this one? I don't know. I know it's a lot. Just keep going, right? Really, like this is your first step. Here's your second step. Here's your third step, right? The second step and you get down to like here. And then there's your third step. And then there's, your fourth step is getting that and plugging it into Fn. And then fifth step is like solving for what you want to solve for. So it really does actually kind of go in certain order. Okay, so just keep that in mind. But then sometimes I can throw new weird stuff at you, like in this one, because I'm a physics teacher and that's what I do. I just throw weird stuff at you and I try to mess you up because I'm a little bit evil like that, right? All physics teachers are just a teensy bit evil, and something to keep in mind. So we have a 250 kilogram piano. It's being slid off the back of a truck that's 0.8 meters high and down a ramp 2 meters long. Okay, we've never been given like information like that, so that's kind of weird. The coefficient of friction between the piano and ramp is 0.15. So we have coefficient of friction, we have the mass, and we have two lengths, which is weird, we never get those. A rope is attached to the piano to help lower the piano down the ramp. Okay. So the tension in the rope is 310 newtons to determine the acceleration of this piano. Let's try to start by drawing our free body diagram and then seeing maybe, if something is missing. So here's my beautiful piano. What do you know? It looks like a box. So there's my piano. What is at work here? Well, we know that there's a rope attached to the piano to help lower it down the ramp. So basically what the rope's trying to do is help lower it, but not lower it, with just what gravity would do, because that would suck. So here's my force of tension. Okay, because it's being lowered by the rope. So it's being slid off the back of a truck that is, okay, blah, blah, blah. Coefficient of friction. Okay, so here's a question. Which way is friction moving? So remember, which way is the piano actually moving? It is moving down the incline, okay? Because they are trying to help lower the piano down the ramp. They're not lifting it up the ramp. They're just helping to lower it. So what's weird here is force of tension is up, but so is force of gravity. Not force of gravity. What am I talking about? Force of friction. Because, again, force of friction always opposes motion, and this guy is moving down the ramp. So force of friction is going up the ramp. We have our normal force as per usual, perpendicular. Yay. And then, of course, our force of gravity going straight down here. Okay. So what's really pulling this guy down the ramp is this force of gravity. And because it's so heavy, of course, then we know that it's a monstrous force of gravity because it's a 250 kilogram piano. And that's why they need to use that tension force, because they don't and they just let it roll down the ramp, well, then there goes your piano. It's down the ramp, but it's probably not doing so well and really hurt too. So as a piano owner, I am all for, not letting gravity just work on a piano and trying to counteract it. So there's one important thing that we're usually given that we're not given here. Do you see it yet? No? It's this thingy. It's the angle. Usually we're given the angle, and we're not given it here. So what the heck? Maybe that's why we're given these weird lengths. Just maybe. Because it gives us how far off the ground it is. It's 0.80 meters high. And it tells us that the ramp is 2 meters long. Oh my goodness, can I find this angle with that information? Well, I got a right angle triangle, I got the opposite side, and I got the hypotenuse, so I would say yes. I would say absolutely let's use sine and figure out what the heck this angle is. Okay? So we know here sine of theta is going to equal opposite 0.80 meters over hypotenuse 2.0 meters. Okay, so my angle is the inverse sine of that. So what is my angle? It's 24 degrees. Okay, so just something, and honestly, would you have seen it right away? Probably not. So that's the type of thing where you would have gotten to the point where you're ready to plug in the angle, and you're like, wait, I don't have an angle. And then it might take you a little bit. So always remember that, yeah, I'm a physics teacher. I'm going to do that. I'm going to try to mess you up because I'm mean like that. So always be on the lookout for how I'm trying to trick you. Okay, so what are we going to do? Well, I don't have a ton of room here, so I'm going to actually go to another page. But before I do that, I can fit this on this page. At this point, I think we can look ahead and be like, I have force of friction happening. I have a coefficient of friction. I'm probably going to need to find normal force. So at this point, I'm going to be proactive and just go right ahead and be like, let's find the normal force first, or at least the equation for it. And then I can go to the X direction and do that. So I'm just going to go ahead, be proactive, do this right now. So I'm going to find the sum of forces in the y direction. So I made the direction of the normal force positive. And of course, going to minus FGY from that. And then of course, like I said, I've never seen it or made a question where it's moving right off the ramp. That would be a totally different thing. So of course, my acceleration in the y direction is 0. Surprise, surprise, this looks exactly like it did in the last one. And the one before that. So yes, your normal force is usually easy to find. If it's on an incline, it's pretty much always mg cosine theta. If it's on flat ground, it's usually mg. The only time it wouldn't be that is if there was a third force acting in the y direction. So always be aware because it might not always be as easy as it's been so far. Okay, do I always still need to see this step? Absolutely. Okay, because you know what? People forget to do this step and then they just say that Fn is equal to mg and they're completely wrong. Okay, we're going to go over to the x direction. Now, I do have a direction of acceleration. This thing is accelerating down the ramp. So when there's actual acceleration happening, I need to make that the positive direction. So down the ramp is positive, okay? And then I'm going to sum my forces in the x direction equals mass times acceleration in the x direction. And hey, that's actually what we're trying to find. We're trying to determine the acceleration of this piano. So yeah, that's what I'm going to find here. So let's sum all the forces in the x direction to begin with. So down the ramp is positive, and the only thing going down the ramp is force of gravity in the x direction. So let's start with that one. Force of gravity in the x direction is positive, and then from that I'm going to subtract force of tension and force of friction. And that's equal to m mass times acceleration. I'm just going to call it a now instead of ax. You guys know it's the x direction. Okay, so again, kind of just keep breaking stuff down until you can't. We know force of gravity in the x direction is mg sine theta because, of course, this is opposite of the angle. Minus the force of tension, which I believe we're given. Let's double check. Rope is attached to help lower it down the ramp. The tension of the rope is 310 newtons. Okay, so we're given that. Good. Force of friction we know is mu Fn, which furthermore, we already know Fn. We found that, didn't we? So let's just go right to what we know it is. Mu Fn, which we figured out. Fn is mg cos theta. See? So that's why I did it first, because I was like, I feel like I'm probably going to need this. Okay, yes, this looks like a total monster, but like go through it and say, what do I have and don't I have? Right, so this might be the situation in which you realize, I don't have an angle. But we already found it because I've done this question before, so, you know, I can kind of look ahead. So mass, do we have that? 250 kilograms, good. G, of course we have that. Angle, this is where you would probably freak out and be like, I know I have an angle, and then you would like read it for 2 minutes, and then you'd finally figure out, oh, I can find the angle. So we do have that. Tension, yes, we have. Mu, do we have mu? Do we have, yeah, 0.15. mg, I already went through that. Yeah, we have everything. That is so nice. So I can go ahead and solve for acceleration. I need to divide both sides by m here. Yes, I'm going to write the whole thing out for a very important reason, because again, people want to cancel out m's when they can't, which I understand because I've so far given you some really nice situations where you could just cancel stuff willy-nilly, and it's been so wonderful. And people here want to cancel m's, and oh my goodness, you cannot. Because like this ft here, does it have a factor of m? Is it being multiplied by an m? If it is not, you absolutely cannot cancel m, because that is not how you do canceling. Okay? This, by the way, this is a total aside. You do not have to write this. Okay? But this is equivalent to this. Oh my goodness, I can't believe I'm going to actually write all this out. This is so much writing, you guys. Don't worry about ever having to write this. But, so yes, the m's cancel here, they cancel here, but it doesn't cancel here. There's no m to cancel with. Okay? And really, why would you simplify it to that once we're ready to plug numbers in? That's not really simplifying, that's just writing more at this point. So, unless m goes into every single term on the top of the fraction, you cannot cancel it out. Okay? Goes into 2, but not all 3 of them, so just don't do it. There's my rant for the day. Okay, I'm going to write all this out and it's going to be a monster, so I'm just going to shut up and do it. Oh my goodness. Okay, you go through all that. You type that into your calculator. Please do this in steps. Okay, don't try to do it all at once. Bracket 250 times 9.81 times sine of 24 end bracket. Minus 310 minus bracket 0.15 times 250 times 9.81 times cosine 24 and all the bracket. Press enter on your calculator. Then divide by 250, please. And then you should get 1.3 meters per second squared. And again, I would suggest don't take my word for it. Well, this is take my word for it. It's definitely the right answer. But go onto your calculator right now and try to plug that in. See if you get 1.3. Okay? It really, 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 really sucks to do a question this long with this much work and do everything correct except for type it into your calculator wrong. Okay? That is really not fun. I don't want you to have to experience that, especially if it's on something like a numeric response on a test. So please, that's also a skill, is typing stuff into your calculator. So go type it into your calculator, and if you don't get 1.3, go back and look what you did wrong. Okay, I know that was a lot. So I would suggest you just start doing questions. And then you come back and watch, maybe one of the examples on here again that's something like the question, and kind of just keep doing that. Go to a question, come back to this. Go to a question, come back to this. Do the kind of steps that I gave you. And then, of course, if you get stuck where something you're like, oh, no, I don't have the angle or something, then look at the question again and say, what information did it give us that seemed to be useless? And is it actually useless? Okay? But yeah, so this one is going to take a lot of work, you guys. So if you don't do the example questions for this, you're not going to have a good time. So please go do all the work, and good luck.